Okay, let's go ahead and get started. Just an administrative announcement. First of all, there is a class tomorrow. Very exciting. So this is the makeup lecture for the one I missed earlier in the semester at 10 a.m. in Rutherford 103. Okay. That's the, I forget what it's called, the boardroom, I think. Okay. And as we mentioned before, so the last class is, no, do not install. The last class is next Tuesday. The final problem set, which I'm handing out now, is due next Friday at noon. So if you want, you could just turn in that problem set and then pick up your final exam. Very exciting. So final exam, pick up, let's say, in my office, which is 316 on Friday, December 5th at noon. Okay, very exciting. Good. Any questions? I mean, yeah, so I guess as I mentioned, it'll be open book, meaning you open your textbook, but no other textbooks, no other resources aside from your textbook. Or the notes from this class. So your notes from this class, all of my handouts, all of my lectures, all of my lecture notes, the textbook, but no other resources, no other textbooks, no internet, no papers, know your friends, know your enemies, that kind of stuff. Okay, good. So let's continue with where we left off last time. So we were considering the theory of a spinner, so a Dirac fermion, with the usual quadratic action, which, unlike a scalar, is linear in derivatives rather than quadratic. And classically, this Dirac fermion will obey the Dirac equation. And last time we worked out an explicit expression for the propagator, that is to say the two-point function. And this, because a Dirac spinner is a four-component object, this is a 4x4 matrix, usually denoted S. I actually don't think the textbook uses that notation. I actually don't know if the textbook uses any notation for the propagator of a Dirac field. Usually we denote delta by the propagator of a scalar field and S by the propagator of a Dirac field. So this is the time-ordered expectation value of psi bar. So here, although it's a 4x4 matrix, I've left off the spinor indices. If you like, you would write this as psi alpha beta, where we have, 4 indices for the first psi and 4 for the second psi bar. And last class, we derived an explicit expression for this propagator in momentum space. So it's a 4x4 matrix that's given elegantly in terms of this Dirac slash or Feynman slash notation. So it's P slash plus M divided by the usual expression for a scalar propagator. So if you didn't have that P slash plus M in the numerator, this would just be the normal propagator of a scalar field. But because the Dirac equation is a linear differential equation rather than a quadratic differential equation, this propagator in momentum space has to go like 1 over p instead of 1 over p squared, because it's the inverse of the equation of motion. And as we worked out last time, the quantity that goes like 1 over p, indeed, is this thing right here. Okay. And indeed, I invite you to check that in the same way that the Dirac equation squares to the Klein-Gordon equation, the Dirac propagator will square to the usual Feynman propagator of a scalar field. Okay? That's quite easy to check in momentum space, and I invite you to do that. Okay, good. And this, the idea is that this is the inverse of the Dirac operator in the sense of Green's functions. So, for example, if you acted with the Dirac equation on this guy S, so S is a function of both x minus and y, so if we just take x derivatives here, then what you'll get is a four-dimensional delta function that sets x equals to y. So that's the usual formula for a Green's function, but now it's a matrix Green. It's both a 4x4 matrix and a function of x and y. So it's a 4x4 matrix worth of Green functions. Okay? And we derived this expression for the propagator in two different ways. So we derived it first by using the explicit expression for the expansion of psi in terms of raising and lowering operators. So those are the ones that we called A. So A and B were the two annihilation operators, the ones that remove an electron or a positron respectively, with momentum P and spin S. And there's an expression for psi that we wrote down last class in terms of raising and lowering operators. And then it was just a reasonably straightforward procedure to go ahead and compute this time-ordered expectation value. And the only subtlety in that computation is that there are a bunch of funny minus signs that appear, and there are more funny minus signs that will appear today because we're considering fermions. Okay. Hang on. Okay, my computer is working. Is that thing not working? Damn it, it's flashing again. Has this happened? Okay. What? Okay, I don't know what's going on.
Green light.
Green light.
Supposed to be on.
What's that?
There's like a second light supposed to be on the screen when it works.
There's a second light that's supposed to be on. Okay.
Next to the red is the blue.
This ready lit. I mean, the lamp light is red. That doesn't look good. Okay. I mean, should I just, like, forget about it? Does anyone have any bright ideas?
Next to us.
I think the projector's just
The projector's just burnt out. Okay. Okay. It's kind of a shame, because it's sort of nice having like, written up lecture notes and stuff, but okay, that's what the textbook is for. Okay. Yeah. I should complain. I don't know, I sort of, yeah. I should complain. Okay.
It's probably the reason the projector in the class before this.
It probably just gets overheated or something like that. Okay. Should we give it a try, or should we just
The
give it
green
a
lights on.
Green light's on. What do you think? I mean, didn't we go through this before? And like it worked and then it stopped working? Okay. Let's see. Okay, now that looks like it's doing. What should we do? What do you think? Should we take a vote? Should I use the projector or should I just go ahead and Blackboard? Okay, I'm just gonna. I'm not gonna waste time. What's that? It is working. Should I try and use this thing? Okay.
Keep on going until the next time it fails, then just go straight to
The next time it fails, I'm just gonna go straight. Okay, good. Okay. Yeah. I would like to write down the Feynman rules for QED at some point in this class. Okay, good. Okay, so we derived this expression for psi both in terms of the raising and lowering operators as well as using the path integral. Okay. Wait. Okay. So the path integral formulation for spinors is just like it is for scalar particles. The only difference being that we need to introduce sources that couple to the spinors, which are Grassmann variables, that is to say, anti-commuting instead of commuting. Okay. So here I'm writing down the expression for the action, and I'm including these two terms here that couple psi and psi bar to eta bar and eta respectively. And last class we worked out, or rather we sketched a derivation of this. So this is just essentially a Gaussian integral in over the variable psi and psi bar. And it's given by an expression that's very similar to the one that we derived with scalar field theory. So in that case, the generating function for a real scalar field took the form of e to the integral d4x, d4y, j of x, propagator x of x minus y times j of y. And here we have a nearly identical expression involving s. The only difference being that these etas are anti-commuting variables, so that when you go ahead and use this to compute correlation functions, there are various minus signs that appear. And one of the goals of this lecture today is to try and sort out all of these minus signs once and for all, so that we can just develop some rules for computing Feynman diagrams with fermions that we can just remember, and then not have to muck around with Grassmann path integrals too much more. Okay? At least not until we get back to gauge theories. Okay. So we can extract correlation functions by taking derivatives of this with respect to eta and then set eta equals to 0. So we need to take functional derivatives with respect to these variables eta and eta bar. Okay. So in particular, every time you want to compute a correlation function with a factor of, say, psi bar inserted at point x, then what do? You take a functional derivative of this generating function with respect to eta inserted at point x of this generating function, and then once you're done taking all of these derivatives, you set eta and eta bar equal to 0. Okay. So every time you want an eta bar, you take a derivative with respect a psi bar, you take a derivative with respect to an eta, and every time you want a psi, you take a derivative with respect to an eta bar. Okay. And because there's this I out front here, you need a 1 over I, or a minus I, in front of both of these. And there's one final subtlety that arises because these etas are Grassmann variables. Okay? So eta is a Grassmann variable, which means that the derivative with respect to eta is a Grassmann variable. So you're taking the derivative of this term right here to bring down factors of psi and psi bar. And when you take an eta bar derivative to bring down a factor of psi, you're hitting the derivative on an eta bar that's in front of the psi. Okay? So everything's fine there. But when you take an eta derivative to bring down a psi bar, you need to commute. You want to hit that psi, that eta right there. So you need to commute the d by d eta bar, the d by d eta through that psi bar here. So you actually get a minus sign here. Okay. And the projector's gone. Okay. So what that means, okay, I'm going to put that minus sign right here in the notes, because otherwise, there, minus sign in the notes. So what that means is that, so if you want to compute, so we have this expression for the generating function, so you have an eta bar psi plus eta plus psi bar eta. And then, for example, if you want to compute a correlation function involving a psi bar, you need to take a derivative of z with respect to eta. So, but because that d by d eta needs to get commuted through this, so a psi bar, it needs to get commuted through this psi bar. So you actually get a minus, you need to insert a minus sign there. So, and for psi, you have a 1 over I times d by d eta bar. So let me just give you an example to make this all explicit. So the example that I'd like to give is, let's just say that we want to compute, say, a 4-point function. So for example, let's say we want to compute, say, a 4-point function. So let's try a psi bar, psi. Okay. So let's say we want to compute this guy in free field theory for a free Dirac fermion. So what do you get? Well, you need, for every time you have a psi, you have a 1 over I d by d eta bar, so eta bar at x1, and then you have a 1 over I to compute this psi bar with an eta at x2. So I'm just writing subscripts on these etas rather than just to keep the notation a little simpler. 1 over I d by d. I mean, at the end of the day, we're going to get 4 1 over i's, so otherwise known as 1. So I'm just going to leave out all of those 1 over i's. And you're going to get 2 of these minus signs coming from these 2 psi bars, which are going to cancel. So you just get 4 of these guys, d by d eta at x3 and d by d eta bar at x4. And you have to take this correlation, apply these functional derivatives to this generating function. You have to normalize everything to set the VEV of the ground state equal to 0, and then evaluate that at all of these etas and eta bars equal to 0. And then we can then just go ahead and use the expression that I wrote down earlier for this generating function in the free field theory. So we had an integral d4x, d4y, eta bar of x, s of x minus y, eta of y. And so if you just go ahead and plug that in, well, you'll see that so you just need to expand this to 4th order. And you just need to be a little careful with how you reorder things. And basically what you'll get is exactly what you would expect from Wick's theorem. Okay? In particular, when you calculate, say, a 4-point function, then you get the sum of all possible 2-point functions you can get where the various pairs of fields are contracted with one another. Okay? Now, a priori, there are many different ways of contracting these fields together. So for example, the first term in this sum is just going to be a psi1, psi2 bar, and then a psi3 bar, psi4. And then you would expect other sorts of terms. So for example, you might expect a psi x1, psi x4, psi bar x2, psi bar x3. But that vanishes because the 2-point function of psi or psi bar is equal to 0 just because of charge conservation. So the only other non-trivial term you get is going to be a psi1, psi bar 3, psi2 bar, psi4. And the important subtlety is that when you work it all out, there's actually going to be a minus sign there. So a minus psi1, psi3 bar, psi2 bar, psi4. And that basically just occurs because you've switched a psi 2 bar and a psi 3 bar, and they're Grassmann variables, so you get a relative minus sign here. So just as when we were considering the definition of time ordering, there was a minus sign there. When you have Wick's theorem for fermions instead of bosons, there are various minus signs that appear each time fields get exchanged. Okay. Good. So that's one of those minus signs that I wanted to talk about today. Are there any questions on this? So this sort of concludes what I wanted to say about free Dirac fields. What we really want to do, and what I'm going to focus on for the rest of this class and all of next class tomorrow probably, is how we can use these fermionic path integrals to derive Feynman rules for fermions, for interactions between fermions or fermions and bosons. And this will include the Feynman rules for QED, as well as the Feynman rules for another theory that I'll introduce momentarily called the Yukawa theory. Any questions before I do so? Everything's going to, so if you like, to some extent, this is just going to be a review of how we derive Feynman rules from path integrals. But they're going to be, the only difference being that there's some more indices that are going to appear than when we were considering scalar field theory, because we're going to be talking about spinors, and a few extra minus signs because of fermions. Yes? Not in the standard model, but in other sorts of theories, one can write down fermion-fermion interactions. So, for example, in effective theories that you might be interested in describing, you could talk about fermion-fermion interactions. So, for example, obviously, electrons could scatter off of one another. The way that we describe that sort of fundamentally is so charged particles can scatter off of each other by the interchange of gauge fields. Gauge fields, or photons, are massless, and so it wouldn't make sense. So it doesn't make sense to view that as a 4-point interaction. But if, say, you had two fermions that could scatter off of one another via the interchange of a very, very massive particle. Remember that correlation functions fall off exponentially for very massive particles. So if you look at that sort of from a low energy or long distance point of view, it would essentially look like a 4-point interaction between those two particles scattering off of one another. Okay. So for example, if you have, I don't know, things like W and Z bosons, which are the force carriers for a weak nuclear force. They're gauge fields. They're massive rather than massless. So that means that at very low energy, you could think about this as some effective 4-point function interaction. So in the olden days, before people knew the standard model, they talked about these sorts of theories. And in many cases, there's a lot of very important and interesting physics that you can extract from them, even though they're not even though it's not the true correct standard model per se. Good question.
I have a question.
Yes.
If we had two different Grassmann variables that we call, say, theta 1 and theta 1 bar, and theta 2 bar, and you had something like theta 1 bar, theta 2, you could move those past each other without inducing a minus sign.
No, they still anti-commute. It sounds like you need to do the problem set that's being handed out this week. Yes. No, they still anti-commute with one another. Right? Because, yeah. That's what it means for variables. So the rule is that Grassmann variables always anti-commute with one another rather than commute with one another. Good question, though. That's a very important point. So in this next problem set, you'll have a lot of practice. Yes. But for example, Grassmann variables and normal variables always commute with one another. Grassmann numbers and normal numbers always commute with one another. And a pair of Grassmann numbers acts like a normal number. Okay? Just like a pair of fermions acts like a boson. If you have a bound state of two fermions, it'll act like a boson. That's responsible for superconductivity, for example. Any other questions? That's a very important.
Yes, something I thought I need to use something that I'm obviously misremembering what he did last week.
Okay, yeah. for example, we used that when we derived this minus
Yeah.
sign
Well,
because
that's what I
eta
was
was
asking
commuting.
about,
Yeah,
like,
exactly,
why that?
exactly. That's just the definition of what we mean by a grasping variable to some extent. Good. Other questions? Okay, good. Okay. So before diving straight into quantum electrodynamics, although we certainly could, what I'd like to do is spend a little bit of time studying a theory which is a little bit simpler, fewer indices to talk about, and in some sense is almost important, that's known as Yukawa theory. So this is a theory of a real scalar field, phi, and a spinor field, which, well, we'll consider the case of a Dirac spinor, psi. So this theory is incredibly important. So for example, it's one of the theories that can be used to describe the effective theory of the strong nuclear force if you're looking at very low energies. So in that case, the scalar fields create particles that are known as pions. Sorry, I guess that's ions, right? And the Dirac spinors describe the various nucleons. So for example, proton, neutron, and so forth. And so back in the olden days, this was, and indeed still a great description if you're looking at low energy physics, this was the theory of the strong nuclear interactions. The theory of protons and neutrons interacting via the exchange. This also, Yukawa theory also appears not precisely in the form that we'll consider today, but in a slightly modified form in the standard model, where the scalar field is known as the Higgs boson. And the spinors are all of the spinors of the standard model. So any matter field, such as electrons, quarks, and so on and so forth. Now, in the standard model, all the various fermions are represented by Weil spinors, not by Dirac spinors. So it's a few of the details are different, but this is basically the physics of what goes into the standard model. So the Lagrangian just describes a massive scalar field. So I'll call its mass capital M, interacting with the Dirac fermion. And if you think about it, there's exactly one interaction that you can write down, which is cubic. It has to be a scalar, so that means that it has to involve two of these Dirac fermions. It has to involve both a psi bar and a psi, both because that's the only Lorentz scalar that we can construct, and also because it conserves charge. Remember, psi has charge plus 1, psi bar has charge minus 1, times a scalar. So I'll call that coupling Y for Yukawa. And then you could go ahead and just imagine studying scattering amplitudes or computing correlation functions in this theory by computing a path integral, a generating function, just as we did for a real scalar field. So in this case, what we want to do is introduce sources for both the fermions and the boson. So this is going to be the integral over all of the fields in the theory of the action plus all of these various source terms. So there will be a source that couples J that couples to phi, as well as sources that couple eta bar that couples to psi, and eta that couples to psi bar. And then we can go ahead and, imagining that Y is a very small parameter, work out systematically the perturbation theory in terms of Feynman diagrams, order by order in the small parameter Y. Yes?
What's the must dimension of Y?
Y's dimensions. A spinner, that's a spinner has dimension 3 halves. So yeah, that's a great question. The easiest way to see that is to note that the Lagrangian has dimension 4, and the derivative has dimension 1, so that these spinners must each have dimension 3 halves. The scalar has dimension 1 because there's 2 derivatives here, and so that means that y is dimensionless, and this object is dimensionless. Good. Yes. Probably should have given you a problem where you worked out all of that on the problem set, but it would have been too easy. So, good. Other questions? Great question. Okay. So we can now go ahead and play the usual game. So if y is equal to 0, we know how to compute that path integral exactly. And functional derivatives with respect to eta, eta bar, and j just bring down factors of phi, psi bar, and psi, so that if you want to calculate this path integral perturbatively, what we'd like to do is imagine taking this coupling term in here, expanding the exponential in powers of y, and then every time you have a psi bar, psi, or phi, you replace that with a d by d eta bar, and d by dj. You take that out of the path integral. You compute the free path integral, and then you're left with this expression for the full generating function. So you have to you have a y, and then you have these 3 functional derivatives. You get a d by dj, a d by d eta, and a d by d eta bar. And I should really be a little careful here. So this guy has a spinor index. This has a spinor index, and this has a spinor index. They're contracted with one another. So that means that the spinor indices of these guys are contracted with each other as well. Okay. Usually when we contract spinor indices, you write the eta bar before the eta. But I'll just put these spinor indices there explicitly, just to remind ourselves that we contract these spinor indices. And this has to be acted on by the free generating function. And what is that free generating function? Well, okay. It's exactly this thing along with an analogous term eta bar of x, eta of y, plus an analogous term involving the scalar propagator. I mean, so far, everything I've done is just repeat line by line what we would have said in the scalar case. And this leads to Feynman diagrams exactly as it would in the scalar case. So what we can then do is go ahead. So as you can see, we have explicit expressions for the propagators. This will just give you an interaction term in your Feynman diagrams, a cubic interaction term between a scalar and 2 fermions. And the derivation of these Feynman rules then proceeds exactly as it did in the case of the scalar field theory. So what I'd like to do is just spend a few minutes writing out those Feynman rules very clearly in the case of Yukawa theory. First in position space if we want to compute correlation functions, and then again in momentum space if we want to compute scattering amplitudes. While I'm erasing here, are there any questions? No questions? Okay. So the notation that I would like to use is, first let's consider the position space Feynman rules. So let's say that we're interested in computing a correlation function. Then what I'll do is I'll use a solid dot to denote a source, a solid line to denote a spinner, and a dotted line to denote a scalar. So this will be the scalar propagator, and so this would be a spinner propagator. And just as in the case of a charged scalar field, we actually need to put arrows on these spinner sources and propagator lines to denote which direction charge is flowing. Remember, the Dirac field has charge, and so we need to distinguish between psi and psi bar. So, for example, if this arrow here is pointing to the left, that means it's the two-point function for a psi over here and a psi bar over here. And the interaction vertex, of course, will conserve charge. So that just means that this arrow has to, there's one arrow coming in and one arrow going out of every interaction vertex. And in position space, all of the endpoints of these various diagrams should have little labels indicating where they're located in space-time. Okay, so we would have to put, say, we would have to denote the position here of the source, and then say the position right there, and then there would really be positions everywhere. Just to keep the notation sort of simple, I won't actually write them all out explicitly, but hopefully you remember how that goes from our discussion of position space correlation functions for a scalar field. Now, most of the time we'll be working in momentum space, so we don't necessarily need to get used to writing position space labels at the end of all these propagators or interaction vertices, but in principle they should be there. Question? That's exactly, okay, so that's what I was going to say next. Okay. So, of course, there are also other sorts of indices floating around. The spinners all have indices. So, for example, if you have an external source that's a spinner that carries an index. Likewise, the spinner propagator is actually a matrix. So, secretly, I should put a spinner index here and two spinner indices here, as well as two spinner indices there. Of course, you'll never get anywhere if you write down all of your spinner indices all of the time. So usually, if it's clear from context, we'll just suppress the spinner indices as well. Good. Okay. So you can then go ahead and we've derived all the formulas for these things. So for example, the scalar propagator is just given by that Feynman propagator. So between points x and y, you get the position space propagator delta of x minus y. Similarly, this is s of x minus y. If you wanted to write down the propagator going with the arrow pointing in the other direction, so this is a propagator with the arrow pointing that way, that would describe, say, an electron going that way, or a positron going that way. If you reversed the arrow so that charge flowed in the opposite direction, it would be a positron flowing this way, or an electron flowing that way. And in that case, just as in the scalar field case, the charged scalar field case, the propagator would be an S bar rather than an S. And finally, we have this interaction. You can just read off what that interaction is here. It's I times Y. And of course, it has spinner indices, but the spinner indices are trivial, just because we contracted the psi and the psi bar together here. So this is really a 4x4 spinner matrix, but that matrix is just IY times the identity matrix. When we talk about QED, it's going to be a non-trivial matrix, but here it's rather simple. Okay, so you could then just go ahead and use these rules to start working out to start evaluating explicitly what this generating function is. So, for example, so let's only write down the connected part of the generating function. So there's all of the stuff that would come from disconnected diagrams. Remember that this partition function is the sum. This generating function is the sum of all diagrams, which we could write as the exponential of, let's say, the sum only of connected diagrams. Any disconnected diagram can be written as a product of connected diagrams. And remember last time we worked out all of the symmetry factors and showed that if you just exponentiate the sum over all connected diagrams, you get the set of all disconnected diagrams. So let's just focus on the connected diagrams for now. So if you work out the sum of all connected diagrams, well, the first non-trivial connected diagram, in addition to all of the various free stuff, the stuff that you would just get for free from the Wick contractions, involves two fermions and a boson. It looks like that. And then there are various terms. So here, I hope I'm going to be able to successfully write down all of the various terms that contribute to the connected propagator up with 4 or fewer sources. So this is one with 2 fermion sources and 2 boson sources. And then there's one more diagram with 4 fermions. So that would describe the scattering. So say in the Yukawa theory that describes the nucleons interacting via the exchange of pions. This is the diagram that you would use to compute, say, the scattering or the force between protons due to the nuclear force, okay, via the exchange of pions. So that's the amplitude that you would compute there. And then there would be various other terms that are higher order in, well, first of all, both in loops. I've only written the tree diagrams here, and in number of sources. So we could then go ahead and start computing things. So let's just, as an example, let's calculate, say, a 4-point function with 2 fermions and 2 bosons. This might be relevant, say, if we were studying the standard model, if we wanted to look at, I don't know, an interaction between 2 Higgses and 2 matter particles. So let's just focus on the connected piece. So we then just need to take some derivatives of this generating function. So we have a 1 over z. And then every time we have a psi, we need a 1 over I times d by d eta bar. So let's put these at x, y, z1, and z2. And then you have a minus 1 over I because of that psi bar. Remember that ordering. That came from the ordering of the anti-commutation of the derivative of y. And then we have a 1 over I d by dj z1. and a d by d j of z2, all acting, well, on z3. Or sorry, all acting on the generating function. So at leading order, the leading contribution is going to come from this diagram. And what is that diagram? Well, let's just write it out using our Feynman rules. Well, so you get two factors of the coupling. So you get I times the Yukawa coupling squared. And then, so this location is going to be x. This location is going to be y. This will be z1. This will be z2. And you need to integrate over all of the undetermined locations of the interaction vertices in the interior of the diagram. So let's call those, say, W1 and W2. You can integral d4 W1, d4 W2. And then you have three fermion propagators. So you have a propagator from x to W1, a propagator from W1 to W2, and a propagator from W2 to Y, along with two boson propagators. So there's a propagator from W1 to Z, Z1, and a propagator from W2 to Z2. And then, actually, if you think about it, there's another diagram where these guys are connected like that. Okay. That's just going to be given by the exact same sort of expression with Z1 and Z2 interchange. And one of the things that you really want to keep in mind here is that the S's are 4 by 4 matrices. So the order that you multiply them is important. And it's important that I'm multiplying them here in the order that you would get as you sort of move along this, this line, contracting the indices as you go. So you get an S here, and you contract the second index of, so the first index here, so let's just write this all in a little bit more explicitly. So the size and psi bars each have an index. So we usually won't write out the indices explicitly, but I will in this case. And then this would be, say, an S, alpha, gamma, S, gamma, delta, S, delta, eta. So the first index of the S is this guy. The second index of the first S gets contracted with the first index of the second S through the operation usually known as matrix multiplication, and then so on and so forth. So if you want to write this out as a product of matrices, you would just multiply those three matrices together to get a matrix whose two indices correspond to the psi and the psi bar indices here. Good. But it's important that when you write out these Feynman diagrams, you keep careful track of the ordering of these matrices. Yes?
So the propagators are two naturally loaded?
Yeah, I've been a little sloppy here. When you talk about Weyl fermions, we're usually very neurotic about where the indices live. I suppose it's most natural to talk about one lower and one upper index. So I maybe would really write it like that. Okay. And likewise, you would write a psi bar with an upper index and the psi with a lower index. Because remember, you can, one of them is a row vector and the other is a column. So psi is like a column vector, psi bar is like a row vector. So that's, usually we don't actually write out those indices explicitly if we can help it. So I was being a little schematic there, but hopefully you have the idea. Yes?
So all of those S's or some of them before?
They're all S's because the arrows.
Go this way? Even though there's a sidebar and
That's right. That's right. Because remember that S is the correlation function of a psi with a psi bar.
So if we swap them,
Hmm?
if we swap the size and the corporate function,
Yeah, if you swap this, you would get an S bar. Remember, S bar is related to S by a minus sign. Okay. So that's yet another one of those minus signs that we have to contribute. That's actually a really good point. So let's say that you wanted to compute this guy with these swaps. Well, you would get a minus sign that appears precisely because of this. So, yeah. Just because there's another diagram that I didn't write down here, where this guy connects with this, this guy connects with this. The rule being you write down you sort of fix the external points and you write down all possible diagrams that you could find that are topologically distinct. Okay. And so the important point, I guess, as we were mentioning just a second ago, is that the ordering of the external fermions will matter. So, for example, let's just do a slightly more sophisticated or slightly different example. Let's consider 4 fermion scattering, okay, with a 4-point function of fermions. So this is what would describe, say, nucleon interaction due to pion exchange, if you wanted to study the nuclear force using the theory of pions. So let's do, say, a psi bar, psi bar time-ordered correlation function. So there, so I'll just put them at points x1, x2, x3, and x4, and denote those just by subscripts 1, 2, 3, 4. Then what will you get? Well, you'll get ig squared, or iy squared, from the fact that we have 2 Yukawa interactions here, 2 interaction vertices. And again, let's call these points W1 and W2. So you'll get an integral d4 W1, an integral d4 W2. So just to make things more explicit, let me actually give names to the various indices here. So let's call this alpha, beta, gamma, delta, say, the various spinor indices. Then you have first this set of propagators here. So you'll get S of x1 minus w1, S of w1 minus, what do we call that guy? We call it x2. So here, this is the diagram. So this would be x1, x2, x3, x4 here. So we have a psi coming in because the psi going this way because the arrow points this way. Psi bar going out because the arrow is pointing that way. And then, so that'll be the alpha and beta indices. And then we have the propagator delta coming from the interchange of the pion. And then we have 2 more S's coming from the guys on the bottom. Okay. So S of x3 minus w2, S of x4 minus w2 minus x4. And the indices of these are the indices of this latter pair. Okay. And then there are various other contributions that arise because so for example, you could connect this guy, so you could consider this diagram. And this is where you really need to start worrying a little bit about all the minus signs that come when you interchange the ordering of fermions. So in particular, in this case, if I can do the counting correctly. So first of all, this is going to be, that diagram is going to give you exactly the same thing, except with x2 replaced with, sorry, x3, what did I call it? X2 replaced with x4. And you get a minus sign Good. Okay, you get a minus sign because you have to commute. So if you replace x2 and x4 here, you have to commute psi 2 through one of these guys and psi 4 through two of them. So you have three anti-commutations, so you'll get a minus sign here. And if at any point this is unclear, the way that you fix these signs for yourself once and for all is you just write everything out in terms of these derivatives, and you just remember the rule that all of these various derivatives anti-commute with one another. So basically what I had to do is I had to anti-commute these Grassmann derivatives 3 times, which gave me that minus sign. In general, if you're comparing various different diagrams, so when you consider 2-to-2 scattering like this, there are all kinds of different permutations of these diagrams. There are these S-channel, T-channel, U-channel diagrams that we considered in the real scalar field case. The exact same diagrams contribute with fermions, but there are minus signs that occur because you interchange the various fermions when you switch between these different diagrams. And the rule that you need to keep in mind is that whenever you, so when you perform, when you switch up the diagrams like this, you end up permuting the external states. And every time you have a bunch of fermions and you perform an even permutation on them, that means that you get a plus sign, and an odd permutation, you get a minus sign. So that's the rule. Okay. In this case, we had 4 fermions, and we did this swap here, which gives you an odd permutation, so that gave us a minus sign. So the rule is that odd permutations of external states will give you a minus sign. Typically, when we compute these things, we're very often not really concerned about the overall sign of an amplitude, because we're computing something like a probability or a scatter for a cross section, which is an amplitude squared. So those signs are really only important when you have multiple different diagrams that are contributing to the same process, because then they can lead to, well, then the signs will appear when you take the absolute value squared. Okay. So these are the Feynman rules in position space. So we're going to be almost exclusively in this course working in momentum space, because we'll be interested in doing things like computing scattering amplitudes. In the case of scalar fields, we went through in some detail the relationship between correlation functions and scattering amplitudes. So this proceeded by the LSZ formula, okay, where you basically, if you want to compute scattering of n particles, you take an endpoint function, you act on it with a bunch of Klein-Gordon operators, and then you take a Fourier transform. So the same thing goes true for fermions. So if you want to calculate a scattering process between a bunch of fermions and a bunch of bosons, you take the correlation function for those fermions and bosons, you act on them with Klein-Gordon operators for each external boson, with Dirac operators for each external fermion, and you go to momentum space. Okay? goes through exactly as it does for a scalar case, just with a lot more indices. So I'm not going to sort of go through all of those details again, but it all goes through essentially the same. So instead, what I thought would be useful is for me to just write out the momentum space Feynman rules for the computation of scattering amplitudes in complete explicit detail. Are there any questions before I do so, however? Let me see how much time do I, so I lost a little bit of time. Okay, got some time. Are there any questions? One piece of chocolate. Good.
There's also more boxes.
Oh, there's also 2 more boxes. Well, that's much less dramatic. Okay, good. Questions? Okay. So, the first thing that I'm going to do is just introduce a bit of notation. So, when we consider a scattering process with some number of incoming particles and some number of outgoing particles, what we're going to do is we're going to put the incoming particles on the left. And the outgoing particles on the right. Now, all of these fermions carry charge. And so the notation that we'll use is that for, say, an external state, an arrow that goes to the right is going to be the particle, such as the electron, and an arrow going to the left is going to denote the corresponding antiparticle. So, for example, when you want to construct explicitly the scattering amplitude for some process, for each incoming electron, so let's say we have the Yukawa theory where this psi field denotes electrons and positrons. For each incoming electron, you'll draw an arrow like this, going into the Feynman diagram. So here that blob represents the rest of the Feynman diagram. And whenever you have an incoming electron, you need to specify what state the electron is in. So that means you need to specify one of these u's and v's that label the various solutions of the Dirac equation in momentum space. So if you have an electron that has a particular spin, then you need to write down the corresponding u, so that u will depend, say, on the momentum of the electron. So we'll label this by the momentum. And likewise, if you have an outgoing electron, then that will be denoted by a u bar rather than a u. So, similarly, for every incoming positron, positrons are, so incoming particles are denoted on the left. So we need to label it by its momentum. We'll call that P1. And we have to write down the corresponding plane wave state of the positron, depending on what its spin is. So that'll give you one of these V's. There'll be some V of P1. And similarly, for every outgoing positron. So remember that this arrow denotes the direction that charge is flowing. And so arrows pointing this way denote that negative charge, I suppose, that electron is negative charge, in one of the great crimes of choices of notation. Negative charge flows this way, and with the arrow pointing this way, negative charge flows that way, so that means a positron is an incoming particle. Now, very often it's convenient to adopt one sort of unified notation for how you are, what direction you're going to take momentum to flow in a diagram. So, for example, I believe when we were considering charged scalar fields, we had the convention that momentum always flowed from left to right. Okay? Usually the convention that we use in QED is that for internal loops, momentum flows in the direction of the charge flow. Okay. Now that's just a notation because you could always have momentum flowing. You could always say the momentum is flowing this way and just call it minus the momentum that was flowing that way. So that's just a notation. But I think it's useful to just adopt that notation once and for all. Or I should say it's really a convention rather than a notation. So convention is that momentum is always labeled in direction of particle flow. So that, for example, if P1 is the momentum of an incoming positron, then that would actually be called minus P1 because the arrow is pointing in the opposite direction. So that's just a notation. And then we have incoming and outgoing scalars. So for every incoming scalar, we'll have a dotted line, and it'll be labeled by some momentum. For every outgoing scalar, you'll have a dotted line like that. And then the rule is that you construct Feynman diagrams by joining all external particles with vertices and in the case of Yukawa theory, your vertex just looks like that. And it gives you a factor of Iy in your Feynman diagram. And you join the external vertices using these interactions in all ways consistent with charge conservation. Which is to say, we join these diagrams in all ways consistent with the requirement that all of the arrows line up. And then, for each propagator, for each internal line, for each internal propagator, we just include a factor of the Feynman propagator in momentum space. So that was minus I. So if this guy is momentum k, so that's going to be minus I times k squared minus m squared plus I epsilon. And for an internal fermion, we have a minus I times the Dirac propagator in momentum space. you determine the momenta of the internal lines by enforcing momentum conservation at each vertex. So for a tree diagram, this will uniquely determine all internal momenta. Whereas for a loop diagram, we need to integrate over the undetermined momentum. So you just need to introduce some momenta that are undetermined and then enforce momentum conservation. For each loop, you'll have one undetermined momentum, and you integrate over it. And there's always an ambiguity in which momentum you take to be undetermined, but that ambiguity won't affect the answer at the end of the day because it could always be removed by a change of variables in the integration variable you're using. A change of, yeah. And you're going to need to keep track of all of the various spinor indices. So you just multiply spinor indices by following the arrows. So in particular, if you have some sort of fermion line in this diagram, just as we did earlier, you connect up the spinor indices. So let's say you would have a U bar here and a U over here. You'll get a U bar, so that you start on the left because scalars are formed with a U bar times a matrix times a U. So you start on the left. Is that the left? No, that's the right. Okay, sorry. You start on the right with a U bar or a V bar. And you just start multiplying. So for example, you'll get an external U bar here, you'll get a propagator here, and then you'll get a U. So you proceed left. And proceed following the arrow. Good. So that works just fine if you have external particles, but it will also sometimes be the case that you have internal loops, right, that involve fermions. So let's say you had a diagram like that. So this would be, I don't know, Higgs scattering, say. In that case, you just connect up all of these spinor indices, and you just take a trace. So you connect up all of these spinor indices. So every time you connect two spinor indices together, you'll get a propagator here. You could track the upper index of this propagator with the lower index of that one, and again with that one, and again with that one, and again with that one. And if you think about it, that's just taking that propagator times that propagator times that propagator times that propagator. It's a 4x4 matrix, and then you're taking a trace. So you trace over the spinor indices of loops. Again, following the arrows. If these rules seem like a lot, okay, don't worry, we're going to have plenty of practice with them. And by we, I mean you. Don't worry, only 2 more rules left. Where was I? Was I at 10? So again, as in the case of the position space Feynman diagrams, Feynman rules, we need to be very careful when we specify the external ordering of our fermion states. And so you need to include a minus sign, so a factor of -1 for every reordering or for every interchange of external particles. So because we never actually care about the sign of the diagram, we only care about the absolute value squared, the way that you should really proceed is you just fix an ordering of the fermions, and then if you switch, if you interchange any of the two external fermions, you just get a minus sign. And finally, and this is the one rule that we really haven't derived yet, but something that I'll have to derive for you, you get a factor of -1 for each internal fermion loop. So, in order to see why that time is up. Okay. So let me just explain very quickly why that's true. The reason why it's true, so the easiest way of seeing why it's true, I'll use better Blackboard management. There we go. So an easy way of seeing why that's true, let's just consider this 4-point guy again. So this would be, say, Higgs-Higgs scattering via a loop of some fermion. So this diagram, so let's imagine doing this in position space for just a second. Okay. That'll make it a little clearer. So you have, let's call these positions X, Y, Z, and W. Then you have 4 propagators. You have a psi bar propagator, which goes from X, okay, the best way to say this is that this interaction vertex involves a psi and a psi bar here at point X, a psi and a psi bar here at point Y, a psi and a psi bar here at point Z, and a psi and a psi bar here at point W. And what you need to do is then start connecting all of these guys up with propagators. So, for example, you get one S here, well, actually an S bar, but it's just a minus sign. There'll be 4 of them, so it's not going to matter. You'll get one XY propagator by contracting these guys, one XY propagator by contracting these guys, or sorry, a YZ propagator by contracting these guys, one ZW propagator by contracting these guys, and one XW propagator by contracting these guys. But in order to write this as a product of propagators, you need to move this psi bar all the way over here to be next to its friend. And when you do that, you'll see that you have to commute it through what's it? Yeah, oh, sorry. If you want to write it as a bunch of sums of S bars, where you have a psi bar times a psi, you need to commute it by 2, 2, 2, and 1. Okay. So you're commuting it, you have to commute it through 7. Okay. So you're commuting it through an odd number of times. So this will be -1 times the trace of SXY, SYZ, SZW, and SWX. This factor of -1 for each fermion loop is incredibly important. It's responsible for all sorts of really interesting physics.
So, can you say that again? Why?
Okay. So remember that each of these 2-point, so what we want to do is represent this as a product of 2-point functions. And so we have, this is going to be, so the interaction vertex has a psi bar located at positions x, y, z, and w. And you want to perform all the various, you want to perform all the various, how should I say this? You want to write this as a product of Green's functions. It's a product of spinor 2-point functions. And if you do that, you'll see that naturally, well, you get an xy propagator, but you've got a psi bar psi, and then you've got a yz propagator coming from these two, a zw propagator coming from these two, and then what you want is a final wzx propagator, where this guy is contracted with this. But, so that means that you need to move this psi bar all the way through to sit over here, and you get a minus sign each time you interchange these two guys, because they're Grassmann variables, and you always end up with an odd number of interchanges. So whenever you have a loop, so you could sort of, and this works for more complicated loops too. So let's imagine, I don't know. Let's imagine that you had also some 2-loop diagram that looked like that. Okay. If you work through it, you see this. So this is still gets a minus sign, because even though there would be other sorts of interactions in between here, they're all bosons, and so you don't get any other funny minus signs by commuting past those. So the rule is that for every fermion loop, for every closed fermion loop, you get a minus sign. Okay. Good. So let's see. I lost about 10 minutes there, but should I keep going? Because what I wanted to do, having spent half the class writing down these Feynman diagrams, is actually use them and give you some examples. I don't think that's something that I can do in 5 minutes. So I could either write down a couple of examples. Should I take 10 more minutes and do a couple of examples in Yukawa theory, or should I wait till tomorrow? I think that's in the morning anyway. What do you think? Vote? This is not a democracy. What do you? Okay, but we can pretend it is. Okay. Should I just stop here? Go on tomorrow? Okay. Why don't I stop here? We'll pick up tomorrow. So tomorrow, what I'm going to do is just go through a few examples, sample calculations in Yukawa theory, and then I'm going to move on and do some calculations in quantum electrodynamics. So as you'll see, generalizing this for QED is really going to be pretty simple. All we need to do is make the scalar line squiggly. Right? And then take into account the fact that photons have polarizations, and so there's going to be a couple more indices floating around in the game. Good. Okay, I will see you tomorrow.